Here we have a discrete dynamical system for our moose population. Here m sub t is the number of moose population in year t, and the rule is over here, so we have mt plus 1. This is the moose population in the next year, in year t plus 1, minus the previous time population, which is m sub t, is 8%, or 0.08, times the previous population size m sub t. So that gives us the change. And then we have the initial condition. Starting in year 0, we have m naught is 1,000. So we start with 1,000 moose in year 0. And if the moose population increases by 8% every year, and that rule is always in effect, then we can use this rule to calculate the moose population in any future time. So let's see if we can calculate some future moose populations. We have the moose population in year 0, so to calculate the moose population in year 1, we want to use this equation over here with t equals 0. And if t is equal to 0, then t plus 1 is 1, so we have m sub 1 minus m sub t, and t is 0, so we have m sub 0 is 0.08 times m sub t, and remember t is 0, so that gives us m sub 0. Now, we don't know what m sub 1 is, that's what we want to figure out, but we do know what m sub 0. M sub 0 is 1,000, so we can plug in 1,000 for m sub 0, and we have m1 minus now 1,000 equals 0.08 times 1,000, which is 80. So this says that the change in the population from year 0 to year 1 is 80. And therefore, since we started in year 1 with 1,000 moose, we end up with 1,080 moose in year 1. What about the next time step? We know what the population now is in time 1. What about in year 2? Well, to do that, we put t equals 1 in our equation. And when we do that, t plus 1 is 2, so we have the moose population in year 2 minus the moose population in year 1. That change is 0.08 times the moose population in year 1. We now know that the moose population in time 1 is 1,080, so we can rewrite our equation with 1,080 for m1. And so we get that the change is 0.08 times 1,080, which is 86.4. And therefore our new population size, we have to add that to 1,080, and we have that m2 is 1,166.4. In year 2, we've gained a fractional moose. I suppose that doesn't make sense, and if it really happened, we'd feel sad for the mother moose that gave birth to 4/10 of a moose. But let's not worry about fractional moose in our model, but just understand that we'll have to round to get something real. We don't want to round, though, in our model, as that would make the model too difficult to handle. So let's just keep going and continue in this rule. And if you kept doing that, not worrying about fractional moose, you could calculate what you would get in the following year. You could say, well, let's look at what m3 is. And plugging in t equals 2, you get m3 minus m2, right? That's what t equals 2. You get m3 minus m2 is 0.08 times m sub 2, which we know is 1,166.4. And if you do the math, what you'll do is you'll calculate that m sub 3 is 1,259.712. And we could keep going. We could calculate that m sub 4 is, well, I'll use the same rule. I won't do it, but you could do it. And if you did it, you get 1,360.48896. Now, I told you that you shouldn't round, So when using a calculator or a computer, you should keep this whole number, 1360.48896. But you don't have to write all these digits down for your answer on paper. So on paper, it's okay to just say, all right, the moose population in time bin 4 is approximately, let's say, 1,360, let's go to hundredths, 0.49. But later, when you want to calculate m sub 5, you shouldn't use this number. You should use the full 1,360.48896 to keep going. We can plot our results using a graph. And here we'll use t for the horizontal axis, and we'll put m, the moose population, on the vertical axis. And let's just plot our first 4 numbers. So here we have year 0, year 1, year 2, year 3, and year 4. And we have, let's make this be our initial condition of 1,000. And over here we have 2,000 moose. So our initial condition is that times 0 we have 1,000 moose. Now in time 1 we need 1,080. So at time point 1 we need to draw a point at about 1,080, something like right here. And then at time 2, well, we have our fractional moose, right, 1,166.4, so whatever, it's something over here like this. And then at time 3 we have 1,259, so this is getting a little too high, but close enough. And at time 4 we have 1,360 approximately, something like this. So this is supposed to be 1,360-ish. So something like, oh, that's not 1,060, but pretend that that's 1,360 right there. And so there we go. That's our plot of the solution to our dynamical system of the moose, calculating the first 4 years from the rule.